I'm Ben Laufer, and this is recent work on optimization and its neglected normative commitments. My co-authors are Tom Gilbert and Helen Nissenbaum. Optimization is a mathematical function, a paradigm used to approach high-stakes decision, and increasingly, it is a worldview that people use to approach everyday life. Formally, an optimization is a way to relate a set of potential decisions to a specific quantifiable goal, and to use this relationship to identify the best performing decision. On the left, we provide an example of what a formal optimization looks like. Students might be introduced to this notation in an introductory operations research course, or perhaps in calculus. An optimization problem is composed of a decision variable, an objective function, and a set of constraints. The decision is whatever a decision maker is assumed to have control over. The constraints limit the set of feasible alternatives, and the objective is a way of measuring the goal or performance of a given decision. Optimization represents a systematic way to quantitatively choose between a set of decisions. It is formal, it is flexible, and it is widely applicable and used. However, none of this implies that optimization is neutral, objective, authoritative, or legitimate per se. Generally, we argue that a decision that is called optimal or optimized is not necessarily a decision that is ethically justified. So in our paper and in this talk, we discuss two questions that guide our inquiry. First, what are the normative assumptions and commitments that are implicit in the use of optimization? And our second question is, what social problems arise when optimization is used without proper care for ethical considerations? For reference, we define neglect as the failure to take proper care for ethical considerations. By identifying failure modes and emergent problems, we hope that some set of issues can be avoided as certain uses of optimization come to be thought of as neglectful. So now we'll talk through a typical optimization process to give a sense of how optimization is used in the real world as a paradigm and as a decision aid. We've already talked about what an optimization model is. Now we'll situate its use in the real world and its systems. In order for optimization to connect and apply to real systems, there must be some assumptions about how observations and details about the world may be operationalized and used in optimization. This inevitably requires some amount of measurement and problem formulation. Once the optimization is loosely specified, it may be intractable or needlessly complex. So the optimization will often undergo a series of simplifications, approximations, and solving steps before yielding an optimal solution. This solution is then applied to some real-world operational decision. For example, a transportation agency decides how to route its vehicles, or a social media platform decides which posts to amplify on users' feeds. Finally, of course, this decision has some impact on the world. So in our paper, we map out these various steps in an optimization and pick apart all of the non-trivial and ethically thorny decisions that are unavoidable when an optimization is used in practice. This paper is systematic and goes through each of these steps. And in this talk, I'll just provide two highlights. First, we'll talk about the ways that values get introduced in optimization problems while the model is being specified. Optimization requires specifying at least one decision and at least one measure of utility. When considering how to incorporate a value like fairness, for example, into an optimization, there can be a number of ways to do it. So the question is, how are values and ethical considerations specified, and when are they given improper consideration? First and foremost, values can be omitted entirely from an optimization. A criminal risk assessment algorithm optimized only to predict future crime without considering the social impacts, including fairness and other effects of an intervention, omit crucial considerations and may therefore be a faulty and unjustified use for optimization. Even if a value is explicitly given consideration in an optimization, it can be misspecified, meaning that it is given improper treatment, for example, either as a constraint or as an objective. A constraint tends to be a categorical rule determining what choices are feasible and ruling out everything else from consideration. Constraints can be trivial, meaning they are introduced but do not actually change the optimal outcome. When they do come into play, they often lead to a solution that rests on the boundary of a constraint. Objectives, on the other hand, tend to be ways of quantifying utility and tend to evoke a more utilitarian calculation of value. They may require predictions and can often be reductive, for example, by measuring value in dollars. To better understand the different ways that values can be considered as part of a constraint or an objective, consider a transit agency tasked with providing reliable high-speed transportation to residents of a city. Two different approaches to optimizing transport might lead to different results. In the first approach, the city decides to contract duties to a private company. The company agrees to certain requirements. For example, it must provide a certain level of access to low-income neighborhoods. Otherwise, we can reasonably assume the company will optimize for profit, maximize revenue, and minimize cost. In the alternative approach, the city agency itself provides the transportation. As a bureaucratic government entity, the agency might eat up as much budget as possible and aim to optimize for some performance metrics, including access, with the allotted budget. So here, these two approaches to revenue management are vastly different and might lead to different realities for people in cities. As a toy example, this transportation case demonstrates how the same two considerations, money and access, can be treated as either a constraint or an objective in an optimization. Now we'll talk about another failure mode that can arise when applying optimization in real-world contexts. This category of emergent problems arises when optimization neglects to consider multiple agents or stakeholders in a decision. First, when specifying an objective, an optimization might be designed to only serve narrow interests. For example, the interests of investors might be prioritized over the interests of workers or everyday citizens in business decisions. Second, a decision model can formalize power relations by presuming that a decision maker has a certain degree of control. For example, a social media company using algorithms to recommend content to users might assume that they can show any post to a user, even posts from people the user doesn't follow. The user, however, might assume that their choice of who to follow dictates which posts they see on their feed. The algorithmic recommendation implicitly removes some amount of control from users and grants platforms and advertisers more control over curating users' feeds. So in total, we identify 6 categories of failure modes, which I'll list now. Misspecifying values, problematic decision boundaries, neglecting to consider multiple agents, mislabeling and mismeasurement, faulty solution steps, and using optimization as a justification for dubious behavior. We refer everyone to the paper for discussion of these in more detail. Zooming out now, optimization is a widely used paradigm with massive stakes. Optimization methods were first developed for US and Soviet state and military operations, especially the line of optimization having to do with linear programming and other programming problems. Amidst advances in computing, they have reached every corner of institutional decision-making, including operations and logistics, military, and financial decisions. Optimization also lies at the heart of sophisticated machine learning algorithms and is increasingly used for expediting and accelerating scientific research. Despite its widespread use, optimization makes a number of normative assumptions and can cause harm. So now I'll return to the general point. As optimization is used in these various domains, it is crucial to remember that a decision that is optimized is not necessarily a decision that is ethically justified. The use of optimization can make people assume that a decision is the best decision, all things considered, but this need not be the case. There are plenty of careless and neglectful ways of using optimization. Assuming that optimal decisions are good decisions can lead to catastrophic uses of optimization in high-stakes decisions. So my co-authors and I hope that this paper is the beginning of a line of research on optimization and its normative implications. Empirically, there are a number of directions for future research. Studies might observe failure modes in practice or identify new emergent problems not discussed in our paper. Documentation methods like model cards, data sheets, and others might help researchers analyze the setup of high-stakes optimizations and pinpoint problematic assumptions. Finally, as with machine learning and other technical systems, biases can be introduced at a number of stages, and work on fairness and accountability in these systems may prove useful. On the conceptual side, we're keen to think about what ethical norms and standards might guide the use of optimization towards social ends. We're also interested in thinking more about the institutional and system-wide effects of optimization as a practice. Thank you so much for listening, and I'm eager to share this work at FACT.